We're going to talk today about radioactive waste. Up until this point, this class has been mostly fundamentals on corrosion, with some examples thrown in at the end, or more for last lecture on the CANDU reactor. Now, today's lecture is going to be primarily focused on radioactive waste management and how corrosion affects that. This is one aspect of things, but this is going to be a two-part lecture. The first part is going to be going over some basics of how radioactive waste is managed in Canada. And the second part is going to be on some of the specifics when it comes to corrosion challenges associated with with that waste management. So let's get into things. So the nuclear fuel cycle in Canada is a lot simpler than a lot of other countries. In fact, it might be the simplest version of what works. It's all domestic. You have your uranium mining that takes place in Saskatchewan. It used to also take place in the Northwest Territories and Ontario. You've got your refining process, which happens at Blind River in Ontario. So this is a process by which you take your yellow cake produced at the mill and you turn it to UO3, and then you have your conversion process that happens over at Port Hope. This brings you to in this case it's a UO2 for Canada or UF6 for export, and then fuel fabrication. And so in this process, after the fuel is fabricated, it goes through to one of our reactors. There was one operational in Quebec. This is kind of a little bit outdated, but the fleet in Ontario and the one reactor in New Brunswick, and that's how you get your power. So what happens afterwards? So some basic slides on how the actual power is produced. So I think I've shown this one before. The actual CANDU reactor itself this is what its core looks like. It's called the calandria. Each bundle sticks around about 15 to 18 months in the reactor, after which time it ends up in wet storage. At that point, what you're basically doing is you're waiting for the fuel to cool down enough after it's come out of the reactor that it can then be moved to dry storage. So that initial time after it comes out of the reactor, you're going to have a short-lived fission products, increasing the heat produced by the actual fuel. And so that's the idea of keeping it within water. All right, so this is what dry storage looks like in Canada. So this is a facility at the Bruce Nuclear Generating Station. It's maybe think of it like a giant Costco, sort of like size building. And these are going to be concrete casks that the actual fuel is slotted into, and say it's air cooled. So that's all well and fine. The basic message today is that fuel is managed in Canada. It's not a crisis. It's a long-term problem that we should be working on, but it's by no means a crisis situation. So where is fuel currently stored in Canada, or radioactive waste in general? So these are the sites. The big ones that we're interested today, though, are not the sites that fuel is currently stored, which are shown, these interim storage facilities, but these two sites right here, 1 and 2, which are two candidate locations for what's called a Deep Geological Repository. So the idea here now is that the siting of this Deep Geological Repository has certain technical specifications associated with it. So those would be that the repository has to contain and isolate the fuel from the environment, continuous monitoring, and potential for reversibility. So, retrievability. So a lot of other countries do not consider their spent fuel as waste. They'll look at it as a power asset that they can then reprocess and then get further power from. At the moment, Canada has no plans for reprocessing, but should that ever change, the idea is that the actual repository itself should be reversible inherently. It should be retrievable from the actual fuel. You should be able to retrieve it from the DGR. This is the basic diagram of what the DGR itself looks like. So you've got your used fuel bundles from the CANDU reactor. Those then go into a carbon steel container that is coated with copper, electroplated with copper. Those are then placed within a clay called bentonite, which we'll talk about a little bit more in a bit. And those are then placed within deep underground within Precambrian rock, under, and again, one of these two sites that are currently being looked at. So the idea behind this system is what we call a multi-barrier system. So each aspect of the system is meant to play a role in the overall containment of the high-level waste of the spent fuel. So first you have the actual CANDU fuel bundle itself. So the fuel bundle itself is about the size of a fire log. That's often a comparison that's made. Contains 20 kilograms of uranium. Can produce about 100 power 100 homes for a year. So it's quite a bit of power. That's why oftentimes you say, oh, your entire lifetime supply of power would fit in the size of a pop can. Say one of the aspects of nuclear is that you're unlike, let's say, fossil fuels, a nation that uses nuclear power, the entire waste is that nation's job to deal with. Close to burning coal, where you put up a bunch of CO2, it's everybody else's problem to deal with. Tragedy of the commons, if you will. So nuclear used fuel is a potential health risk for is a potential health risk for a very long time. Must be safely contained and isolated from the people in the environment, essentially indefinitely. So the long-lived radioactive products in this will last a very, very long time, on the order of something like 1 million years. So when you're designing one of these DGRs, that's the kind of timeline you're looking at in terms of chemistry. So it changes things quite a bit when you're thinking about the corrosion scenario of these materials. So first barrier associated with the overall system is the fuel pellet. So this is kind of a nice infographic, the size of them relative to a battery. There's sort of a classic image, one of these fuel pellets relative to a quarter. As we're going to talk about later in this lecture, this fuel has a high density. It's a high density ceramic. It's extremely durable and does not readily dissolve. And so because of these things, it acts as an actual barrier itself. So 9 pellets can power an average Ontario home for a year. Again, it's something that's often used as a catchphrase. So this is the actual second barrier here. So this is the zircon alloy. So the zircon alloy is a zirconium, tin, iron, nickel alloy. And so it's what we actually use in our reactors. The pellets are held within these sealed tubes. Metal is extremely strong structurally and is corrosion resistant as well. Next is the used fuel container. So there's quite a bit of engineering that goes into this, and this is sort of intended as one of the main barriers to release. It's durable, long-lived, deep underground, strong steel core, and corrosion-resistant copper. So we'll really go into especially the corrosion resistance of the copper. That'll be kind of the other major topic we'll touch on for today's lecture. So there's some natural analogs. So why are we so confident that in the case of, let's say, copper, that it's a good choice to use? Well, we can see it in the natural environment. There's examples of copper sheets in mudstone from the South Denvin, England, formed 200 million years ago. You can figure that out via radio dating, and it shows little to no corrosion. So this is the kind of indication that under conditions, reducing conditions, you can have a case where this copper can actually survive a considerably longer time than what we're hoping our DGR has to last for. So the next barrier is bentonite clay. So bentonite clay is very, very dense clay that acts as a cation exchange. So any kind of cations that are produced potentially from radioactive waste dissolving, the clay itself acts as a barrier for its release. Naturally swells, fills voids and spaces, reducing sort of air volumes and transport of water through to the container. And if the container fails, the clay acts as a sponge for any of the cations that would be released, particularly uranium or other transuranics. In terms of natural analogs, it's kind of something that's brought up. So these trees over in Italy were buried in clay for 1.5 million years. They're still made of wood and have not decomposed. It's pretty amazing. But that's the kind of shows you how dense this clay is in terms of stopping the outside environmental processes that would otherwise degrade these trees. Next, we have the geosphere. This is the host rock. This one's fairly easy to explain. Natural barrier protects the repository from the surface, natural and human, and isolates the fuel for a very long time. Canada, in some ways, is blessed that we have a very large Canadian shield that acts as a barrier for the release of a stable form to a that is not seismically active compared to a lot of other regions on Earth. Okay, next we have the geosphere. So this is the analog for this. It's often brought up that Cigar Lake in Saskatchewan acts as a natural barrier. So it is the most concentrated uranium deposit in the world, and it has on it this geology that involves a quartz cap in which the actual hydrogeology of the water flows over top of the deposit itself, the ore deposit of uranium. One of the reasons why this uranium was able to concentrate so heavily in this area. It's an example of how that how the geology creates the hydrogeological conditions conducive to maintaining the uranium. Okay, so key suitable host rock characteristics. I'll read these out. It's not going to be the major focus of our work, but you know, if you're in geology and you're looking to cite one of these DGRs or a potential DGR for your country, these are the things that you're looking for. Sufficient volume of rock at a sufficient depth. So you need the right rock and you need it to be at the right depth. Low groundwater movement at the repository depth. So I was mentioning before the example of the Cigar Lake, you want very little water flow through the actual area that you're targeting. Resistant to earthquakes, self-explanatory. Resistant to ice ages. This would be the rock itself. If it's been there for being stable for millions of years, it's a good indication. Resilience to land movement, uplift, and erosion. And then finally, favorable chemical composition of the rock at the repository depth. So this is one's a little bit trickier in terms of what that means, but we'll talk about a little bit about some of these, some of the different the groundwater concentrations that you would find under at least our own DGR locations that we're looking at. All right, so it bears mentioning that we're primarily focusing on these two locations, Ignace and the South Bruce site. But there were many other candidate sites that were examined. This is an important aspect from more a public policy standpoint, but it bears mentioning that when it comes to communities willing to host a DGR, the best practice is to approach, or rather put a call out or approach those communities and ask of their interest. What you typically do not want to do as particularly a Western liberal democracy, maybe authoritarian countries have a different approach, but in Western liberal democracies, you do not typically want to impose this sort of thing on a community. We'll talk about a little bit later about an example of what the Americans tried to do and how it didn't end up panning out so well, partially for the reason of a lack of public consultation and buy-in. So safety analysis approach. So there's a few different aspects of this. When you're thinking about the DGR, there's kind of two different scenarios. There's your reference case scenario, and then there's your worst case unlikely scenario. So in your reference case, you assume that people are living off the land, close to the repository, drinking irrigation of waters from local wells, farming, crop, livestock. Assume that some used fuel containers are defective from the beginning. So these are two assumptions that you bake into your thinking. So you're not thinking these are all containers are going to be resilient from then on. You have to assume that some of them are not going to be, and that there will be people living above and using the actual land. So assuming that you're like in the middle of nowhere, and nobody will ever use that space, is usually a flawed notion. Especially when you're looking at the timelines of a DGR. Worst case scenario, so unlikely, used fuel, more soluble in water. So it's more soluble than you think. Container defect more important. The issues you have, all containers fail with time, and sealing materials more permeable. So that's what you plan for in terms of your worst case unlikely scenarios to have to deal with. So let's talk about corrosion. So that's all fine. We've gone through the basics of what the deal is with the DGR, at least in the Canadian context. When it comes to corrosion, this is really where the rubber hits the road. So I'll just kind of a brief overview again. 5 barriers. You have the fuel bundle itself. and the fuel within it, the actual fuel pellets. Those would be 1 and 2. 3 is going to be your used fuel container, so it's the copper over the carbon steel, with primarily the copper acting as the corrosion barrier. 4, you're going to have the bentonite clay, and 5, you're going to have the DGR itself. For today's lecture, we're going to be focusing on 2 aspects of this. One is going to be this copper coating in terms of how corrosion works with it, and the underlying carbon steel where it can play a role. And second is going to be the pellets themselves. Like I mentioned before, in the scenario, you have to the likely scenario, at least one of your used fuel containers has failed, and so you have to assume that there will be water reaching your fuel at some point during the lifetime of your DGR, and plan ahead for that. So, what are the conditions that we're dealing with? So don't worry about the sort of bottom portion here yet in terms of the different forms of corrosion. Let's focus on what the conditions are in this DGR. So you have sort of 3 things to track here. The first one is your temperature. So over time, what's happening is your temperature range sort of starts off in kind of a broad range, depending on what the deal is with the fuel, its burn up, how many fission products it has, how much heat it's releasing, how long it's been sitting around before it was put within the DGR. So there's kind of a wide range with it that slowly goes up over time for the first 10 or so years, looking out to about 100 years. And then that starts to drop off as fission products degrade, and then you end up going down in terms of temperature. So they're sort of starting with a broad range and moving down. Kind of caps out below 100 degrees Celsius, to give you an idea. But you can be playing in and around like 90 degrees, for instance, is not a bad area to be doing some of your testing in terms of worst case scenarios. Second thing, what's happening with oxygen? So this is deep underground in an area that has inherently anoxic conditions. And so over time, once you open up this DGR, you mine your hole in the ground, you're going to see oxygen start to deplete fairly rapidly. So to give you an idea, there's a log scale, or an absurdly long scale. You're going to see almost all oxygen completely depleted and end up under reducing conditions. So lack of oxygen within 10 years, could be faster, could be longer. A lot of this is going to be eaten up by the corrosion process, as well as maybe mineralization reactions, possibly bacteria living off of it that you may have exposed. But one way or the other, free oxygen in the system will be used up fairly quickly. Third aspect, the radiation dose itself. So when it comes to the radiation dose, the primary way in which this affects your overall container is through the giving off of radiolysis products. So I think I brought this up before. I talked about this before in the last lecture, but just to recap, gamma radiation can actually end up splitting water and forming these different radiolysis products, the nastiest of which, when it comes to our case, is hydrogen peroxide. And we'll talk a lot about hydrogen peroxide specifically within this lecture. So from that, that then gives you 5 main kind of corrosion mechanisms that you're concerned about. There's a little bit more than that, but kind of different aspects of this. But we'll focus on these 5 for today's lecture because they're the most prevalent. First is radiolytic corrosion in humid aerated vapor. So this would be what you would have right at the beginning of the DGR, where you have aerated vapor, so you still have some oxygen in the scenario, in the container area, and you have humidity. You don't have full water saturation, but you have humid air. Second is going to be radiolytic corrosion in an aerated aqueous environment. So this is after this is before you get rid of all your oxygen, but after water has reached your container surface again. We'll talk about in a bit. And then next you have galvanic corrosion. This is what's going to occur if you have some kind of defect in the copper layer and you have a galvanic reaction happening between the steel and the copper. If you remember before, what was let's say the Statue of Liberty, if you have steel bolts on a copper surface, that steel is going to be galvanically corroded. Then you have your corrosion at a defect weld under anoxic conditions. We're not going to talk about this too much, but I'll show you an example, kind of a conceptual idea of what would happen if you have a defect within the sealing weld for this. And then you have corrosion by remotely produced a sulfide. This is a big one. Sulfide is something that you are primarily planning for, and we'll talk quite a bit about that. Okay, let's start off with the first one, which is humid air and aerated vapor. So to begin here, let's think about what the composition of the groundwater is, or at least the water that would reach the surface of the container, because it's not exactly the same as the groundwater. There's some thermodynamic calculations that have to go into what you would actually expect to be at the surface of the container. But what you're looking at is, at least under one of the conditions, this is the one associated with Ignace, Ontario, in crystalline, a host rock. You're looking at your primary ion being chloride, with the cations being sodium and calcium, with lesser contributions towards with sulfate and magnesium and some other minor constituents. That then gives you, in terms of minerals that you would expect, salts that you would expect on this container surface, sodium chloride, calcium chloride, and then this gypsum, and then a little bit of magnesium chloride. So why does that matter? Why do we care about that? Well, under these initial disposal conditions, what will happen is that salt will initially be wet when you put these containers down under within the DGR. There's going to be heat given off, but initially when you put them in there, there's going to be water present, and so you'll have a sort of water droplets formed on the actual container surface, which will very quickly end up being dried out by the heat given off by the container. But over time, as the humidity starts to increase and you start to get closer towards water saturation, you're going to see these points, you're going to see these salts deliquesce. They're going to deliquesce before you hit 100 degrees, 100% relative humidity, where you would just have water present as on its own. And how that exactly happens and what that means in terms of corrosion is an area that needs to be studied. Where this ends up being the biggest issue is going to be likely right where the container itself meets the bentonite. As I'll explain in a second, you get an effect, or you could potentially get an effect where you have a net cathode present and a net anode present on the surface. But we'll simplify this a little bit. So when I say deliquescence, this probably isn't a new term for all of you. But if it is, here's essentially the way it works. Your salts, particularly chlorides, have a certain relative humidity in which they will take up water into their structure and actually dissolve. So they'll self-dissolve under certain humid conditions. This is a process that happens incredibly rapidly once you hit the deliquescence point of that salt. This is a series of images taken from an experiment I did previously. You see the salt itself that was deposited onto a copper layer, and you see that seconds after the relative humidity was increased to 75%, you see deliquescence occur. So it goes from being totally solid to looking moist, and then within seconds you have liquid water present on the surface. So this is a process that can happen very, very quickly in response to changes in relative humidity, but does not necessarily last. Depending on what happens with the corrosion products that build up, you can actually form something that is no longer deliquescent and have it dry out. Okay, so we're going to come back to a way of thinking about this type of corrosion that I've brought up, I think, earlier in the lecture in the overall course. But if I haven't, we're going to go over it from the get-go again, which is the idea of this Evans drop model of corrosion. So the Evans drop form of corrosion is what happens when you have a bead of water on a metal surface. You have a natural gradient when it comes to oxygen concentration. The edge of the drop will naturally have a higher concentration in terms of oxygen than the center of the drop. And so what you end up forming is this effect where you have an anode right in the center of the actual drop, and then it ends up moving out to the surface where the oxygen is present, that you would then be reducing. So oxygen reduction is happening at the periphery. So this would be this reaction right here. Oxygen plus water gives you hydroxide. And then at the center is where you have your anode, your anodic spot, where you're having in this case copper, being oxidized and dissolving into the water itself. And the products you can form, this doesn't necessarily stay as copper ions. It's probably going to form some kind of corrosion product. In this case, it would be atacamite was one that we found, which is this mineral right here. So this process is obviously not good because it's inherently creating localized corrosion. It's not necessarily pitting corrosion like we were talking about in our previous lecture, where you have a passive film that's breaking down, but you have localized corrosion. So not inherently not good in that sense, but this type of corrosion doesn't necessarily last very long in the DGR itself. Also bears noting that as the edge of your drop, you may be having other products form, so there can be CO2 absorption forming this sodium carbonate. Some of the work we found, we actually found this would actually form, and it itself has its own deliquescence point that would change the deliquescent nature of the actual corrosion. All right, so I thought drop is kind of, that diagram I showed you before is kind of conceptual. I figured even though we're not going to go into this for this lecture, this isn't going to be a lecture just about atmospheric corrosion. That could be a whole interesting lecture on its own, but we're not going to focus on that today. But this is, I think, a sort of interesting illustrative example for what this corrosion ends up looking like. So you see here a sample that I have that we performed this work on. The center is where the actual salt was present on this copper sample. So it was deposited on there, allowed to dry, and then brought into the humidity chamber. So you see that copper deposit. In this case, this is going to be atacamite primarily. So that's a copper hydroxide chloride that builds up in the center. And then you have on the periphery where you have your cathodic reaction. So it looks almost clean looking. And then at the edge, you have the other corrosion deposits that are deposited at the edge of the actual droplet. All right, so what about once we have saturation? So that's what things look like when we have humidity present. But eventually the containers will cool down to a degree in which you will build up water. Water will be permanently present on the surface. The whole surface of the container will be saturated with water. At this point, you start off a type of corrosion when you still have oxygen present. So this would be radiolytic corrosion in aerated aqueous environment. This will not last very long. Simplest form, you've got oxygen diffusion through the water. Oxygen is being reduced. Copper is being oxidized. Very quickly after it's oxidized, there'll be a desorption of that copper from the surface, form of a copper ion. Usually that will then complex with the hydroxide itself that's being produced. So this copper hydroxide ion that'll then deposit itself likely on an area where corrosion is building up. So I'll have an area where copper is being dissolved, an area where copper is being deposited. From this point, you can have a buildup of copper oxide, so Cu2O. You may get small amounts of the CuO buildup on the surface, so it'll be it'll maintain a 2+ state, or it can go down to a 1+ state, depending on what's happening redox wise. And then you can also have oxygen at this point itself being reduced. So this is another possibility here, and that can then lead to buildup of more copper too, so copper oxide on the surface of of these corrosion products. The morphology of this can change quite a bit depending on how much water is present. You can have sort of pores or small islands of copper being deposited here, but importantly, this general corrosion is going to be uniform across the surface. We're not worried about pitting under these conditions. And the reason for that is that we haven't reached conditions in which we would actually have a passive film. So this is one of the big takeaways that I want to kind of emphasize for this sort of portion of the lecture, and it'll just become relevant again when we go over the sulfide corrosion. Pitting corrosion can only occur after you have passivated the surface of the metal. You have to have reached passivation before you can form a pit through that passive layer. So up until this point, I've been kind of indicating or suggesting, oh, passivation is good. The metal is protected. You just have to stay in that zone of passivation. That's a fantastic strategy when you're dealing with, let's say, protecting a bridge, for instance. Okay, great. You have, you're maybe you're controlling the conditions of the redox conditions in such a way that you're staying within that passive zone. That's oftentimes how aluminum structures are protected. In this case, though, we're dealing on the time scale of 1,000,000 years, and so relying on a passive coating is a very, very bad idea under these conditions. You want to maintain corrosion in an active state, active but small, uniform state, in order to properly control, properly account for the amount of corrosion your container is expected to withstand. Once you have pitting corrosion, now all those estimates go out the window, because if it goes through the copper, as we'll talk about in a sec, galvanic corrosion can begin, and you quickly have issues, or relatively quickly have issues. So what about if it does go through? Again, you assume that some of these containers will have defects and will fail. So what happens if the copper layer is penetrated? So this is the kind of reactions that you get. It's one of galvanic corrosion. So it's that classic scenario where you have oxygen reduction happening preferentially at the copper surface, and then you have iron oxidation happening primarily at the bottom of your, or exclusively in this case, because that's where the penetration is, the bottom of wherever your copper coating has been penetrated. At this point, there's a series of other reactions that occur. You have buildup of these different corrosion products. I'm not going to test you on any of that, but this is the basic kind of a mechanism that's happening. It's reduction on copper and oxidation on iron. So what does that end up looking like in terms of a defect within the actual weld? These two types of corrosion are the cases where you can, if you have either of these occurring, likely corrosion will progress quite quickly in ways that will likely lead to the failure of the canister. In the case of crevice corrosion, what you have happening is that seam on the head of the container, the copper that's deposited there via sputtering, has some kind of defect in it, and its morphology in such a way that water is allowed to seep into the crevice itself. So the actual the break within the carbon steel where the head is attached, and at that point you have a crevice corrosion due to a residual water in the container at the weld region. So this is very obviously not good. If you have penetration of water continuously through this crevice, through your defect weld, this is then going to lead to the galvanic corrosion. But even if you don't, you're going to experience a certain amount of crevice corrosion along this seam anyway. So next, we're going to be focusing on corrosion due to sulfide. So this is a very, very nasty process, and we're going to take this one slow. But before we get into the kind of nuts and bolts, I'm going to kind of give you the very basic overview. So you have this sulfide that builds up within the DGR due to sulfide-reducing bacteria. So sulfide-reducing bacteria are a class of bacteria that actually use sulfur as its oxygen transport, if you will. So it's actually basically breathing with sulfur, if you will. And so this is a very, very ancient type of bacteria or form of metabolism for bacteria. So you can think of the very first life on Earth living near undersea vents that are spewing sulfur from beneath the earth, sulfate from beneath the earth. And what this is doing is this is actually using this as it's reducing it as it's a sort of its mechanism for breathing instead of using oxygen. So why is this a problem? You have this building up naturally in the DGR. There's nothing we can do about it. This is just, if you have, if you're going to bury these things deep underground, you have to assume there's going to be a certain amount of this bacteria present around the container. And this sulfide attacks copper fairly readily. And in the process, it's going to build up copper sulfide. So that's the simple way of explaining this, but there's a lot more that goes on when it comes to the sulfide corrosion mechanism that has sort of ended up being a lot of the focus when it comes to studying copper corrosion in DGR conditions. So before we get into that, I want to give you kind of a perspective on what we've talked about so far, and then maybe kind of put the emphasis on sulfide in a little bit of context compared to these other forms of corrosion. So what I'm showing you here are 3 diagrams, one for each of the scenarios here. So the copper coating on a steel substrate, this would be as manufactured. So in this case, 3 millimeters of copper or 300 microns or micrometers of copper will be present on the surface of the steel when it's initially manufactured. The current analysis for what kind of corrosion we can expect is shown as right here. So the blue, both the light blue and the sort of regular dark blue, are going to account for radiation-induced corrosion. Then you have it's going to be the actual damage of the material due to the radiation itself being given off. So small amounts, relatively. Then you have we haven't really talked about that in this class very much, but it'll be a damage to the material. Then you have non-uniform oxic corrosion, light green, and then oxic corrosion in green. So these would be what you'd expect under the humid conditions. That would give you a non-uniform corrosion. Again, like I mentioned before, when you have humidity, deliquescence corrosion, it's kind of inherently localized just because of the nature of that Evans drop model of corrosion. And then oxic corrosion, so green. So this would end up being probably uniform across the surface after water has saturated the container, the area around the container. Then I'm going to skip red for a sec and go to purple. So this is your anoxic corrosion. So this is what you're expecting after oxygen has been entirely depleted from the system, and you have very small amounts of corrosion due to the presence of radiolysis products. You're going to have a certain amount of anoxic corrosion. It's not going to be very large, but you can expect a certain amount of it present, and that's shown in purple, so about 100 microns. And then you have the big one, which is sulfide itself. So sulfide corrosion has a fairly wide margin, much wider than the other forms, because the modeling for it relies on how active this sulfur-reducing bacteria will be. We know that there will be sulfate present within this within the DGR. Sulfate is one of the major constituents of the groundwater in these cases. So there's going to be sulfur present as sulfate. What we don't necessarily know is how much sulfur is going to be produced. Sulfide is going to be produced by these bacteria. So our analysis shows that it should be enough to account for about 80 microns worth of corrosion. But there's a very wide margin of error associated, baked into the modeling, because whenever you're dealing with microbes, life is inherently less predictable than just inorganic material. And so you account for quite a bit of corrosion on the actual copper itself. So because of that, the modeling that goes into this has to be very well underpinned by experiments. If you're wondering what orange is, it's a redundancy estimate on top of that estimation of a sulfide corrosion. Again, that's associated with the form of the activity of sulfur producing bacteria. All right, let's move on to some electrochemical measurements. So the simplest way to study this kind of thing is to run essentially a Tafel plot. It's, as I've been emphasizing this entire course, that this kind of very basic electrochemical experiment can tell you a lot about what's going on with your material under the conditions you're interested in. In this case, the big difference is that it's not just a Tafel plot, it's a CV, and so you're still controlling potential, and you're measuring current. In this case, you're just cycling back. So instead of just going in one direction and the other from E-core, you're actually cycling it back from wherever you brought the potential up to down, back to sort of the other far potential. So around kind of where E-core is. So let's talk about what we see if we do this. I wish I could kind of remove this kind of legend for a second, but I can't, unfortunately, for this figure. But let's just focus on what's happening with the black line. So don't worry about what the different hertz are indicating. I'll talk about that in a second, why that's important. But let's just focus on the black line and focus on these 5 regions of the sample itself. So you have region 1 is going to be is going to be the initial looks to be passivation of the material. It's not, but we'll kind of get into that a little bit. So it's corrosion on the surface of the material. And then you have 2 and 3 after you reach a certain point in terms of the potential. So around 2-ish, 0.2-ish volts is when you're going to have an area of a reduction or oxidation of the actual of the material, and then cycling back, reduction of the material under 3, and then finally under 4 you're going to have a reduction of whatever sulfide corrosion had taken place, and then that brings you back to 5. So there's sort of 5 general regions of the CV. So one of the important aspects of this is this has been this kind of general flat region. This looks very similar to what you would expect under passive conditions, right? You have flatness. Okay, that looks like passivity. And so that would be not good, right? That would then indicate that you could potentially have pitting corrosion. Well, one of the main reasons we know that's not the case is that if you have agitation in the sample through rotating the actual sample itself, you see a massive change in the current density in this region of region 1. So why is that important? So if you remember before, there's kind of 2 limiting factors when it comes to corrosion. You can either have a mass transport limitation, or you can have a charge transport limitation. So one of the important aspects when it comes to passive coatings is that you're expecting there to be a charge transport limitation. That passive coating is going to degrade further corrosion enough that the only thing affecting it, controlling corrosion, should be a charge transfer. But instead what we see is we see an effect of mass transport. And we know this because as we rotate the sample more, we're agitating the liquid around the sample. So we're adding more sulfide ions to the surface. We're allowing more of the sulfide ions to reach the surface, and we see an increase in the current density. So this indicates that we do not have a truly passive film. What we have instead is a porous film that's built up. And this porous film prevents sulfide from easily reaching the surface. And when we agitate the sample, we see there to be an increase in corrosion. But importantly, a porous film is not a passive film, and it cannot result in pitting corrosion. So that's the kind of main takeaway I want to emphasize here for this figure, is this dependency we see on this sort of initial set of regions 1, 4, and 5 to agitation of the actual sample. Importantly, I should say that under 2 and 3, we do not see that same dependency on mass transport. You're seeing similar current densities under these regions of the CV, regardless. I mean, there's a little bit of dependency right at the peak for this regions, but in this case, you could potentially have the buildup of some kind of passive film. But importantly, this is under potential regions that are unrealistically high for the overall for the DGR itself. So when I say a porous film is building up, this is what I mean. So you have copper sulfide building up in the form of Cu2S. It's going to be the primary form it takes. And this is going to cover the sample itself, more or less, but it's going to cover it imperfectly. So there's still going to be areas for sulfide to get in, to attack the actual copper surface. This then results in corrosion in the form of a adsorbed copper sulfide, which can then deposit itself through dissolution within the water onto the actual the film, this copper sulfide film. Importantly, you can still be having reactions occurring at the surface with other oxidation products. So if you had already present oxide built up on the surface from the previous corrosion steps that you expected in the DGR, so this would be, let's say, having oxic corrosion happening when you initially buried it, either under humid or saturated conditions, those corrosion products could potentially themselves be further corroded by sulfide. It kind of depends. From a modeling perspective, you shouldn't bet on that. You should bet that only your actual copper surface is going to be corroded. But in reality, a certain amount of these already oxidized corrosion products will likely see an exchange between let's say, hydroxide and sulfide. So this in and of itself can act as a partially protective barrier for the underlying copper, but again, not to be relied on. So this is what corrosion looks like as a model for sulfide. Yeah, so why don't we use it for ILW? So ILW stands for intermediate level waste. I was going to talk about this very briefly at the end of the presentation, but I'll kind of highlight it a little bit now because I was going to talk about it anyway. ILW spans a large number of different materials that require different aspects of management. A big aspect when it comes to ILW management is gas production. Generally, these materials that we're dealing with are not high in carbon; they're spent fuel. They're inorganic ceramic materials, solid materials of some sort. ILW often takes the form of sludge or spent resins, carbon, spent ion resins, and so you're worried to some degree about the breakdown of those resins or of that material such that you have gas production, and you have to kind of account for that when it comes to your container design. The British are kind of noteworthy because they have a lot of graphite in their sort of their classic, reactor designs, gas-cooled reactor designs, and so they have a significant amount of ILW to deal with. And so because of that, you can't be designing. Essentially, Canada's used fuel container design is essentially a giant pressure vessel. It's designed to have a certain amount of pressure placed on it from the surrounding rock and bentonite, and a certain amount of pressure built up within it from fission gas release in the form of, let's say, helium, from degradation of the fuel. That's fine. It's fine in terms of pressure management. When you're talking about large amounts of pressure being produced from the degradation of carbonaceous waste, you have a totally different scenario, and typically you have to plan for that such that you allow the gas to escape somehow. And that has its own set of considerations when it comes to carbon-14 release, whole aspect of that. And you know what, Mehdi, that's definitely the focus of what I've hired you to look into. Canada's depending on you because we have to have a look at this, because now the mandate from on high is that ILW will also be stored in some kind of DGR, and so we have to figure it out. So that's the kind of short answer though, to this. And again, if you have some kind of gas release, once you have galvanic corrosion, you don't want copper next to your steel. You probably want one continuous material. Otherwise, that galvanic corrosion is just going to make things worse. You might as well not have copper there at all. So that generally sums up the Canadian case. In general, at least when it comes to copper, that generally sums things up. There are other aspects that I haven't gone into. Hydrogen is one of them, so you can have the buildup of hydrogen or hydrogen production at the copper surface due to sulfide, a water reduction. That hydrogen doesn't look like it plays a large role from experiments I've done personally as part of my own research. I haven't really gone into it because I don't know. I think it's a little bit sort of besides the point, and it gets a little bit into the weeds. But the basic idea is that you can have reduction of the water at the surface of the copper sulfide, and thus you're not seeing that hydrogen being absorbed into the copper, which was the fear that some people have had. It looks instead as like it does not actually build up readily into the copper due to not diffusing readily through the copper sulfide. So it's sort of a caveat, maybe a little bit of an aside. But that essentially sums things up in broad strokes for Canada. So what about the US? So they have something of a DGR. I'm not sure if it's really it's a repository, but it's got some serious controversy surrounding it. It's called Yucca Mountain. It's in Nevada. It was mandated by US law in 1987 after a few years of looking for a candidate site in a series of different states. The underlying reason it was chosen is supposedly the scientific underpinning of it. I'm not going to prescribe motives for why the US mandated this site specifically, but they did. They said that this was going to be where the Department of Energy, who manages all used fuel in the States, was going to have to put all used fuel for the U.S. And so this was mandated by law in 1987. Importantly, though, this was not done through any kind of public consultation process. I'm not going to get into kind of some of the politics surrounding it, but it is interesting to some degree from a scientific standpoint because there's major differences between this repository and the one Canada is pursuing that are interesting from a corrosion course standpoint. The project, if you're wondering, is like indefinitely put on hold, and the U.S. is now going through the process very slowly of thinking about what it might be doing for a future DGR of some sort. So this is the Yucca Mountain containers as they're kind of, or as they were kind of conceived. The idea is that it would be fuel placed on these pallets, and the fuel itself would be encased in these containers with what's called alloy 22. So it's a high nickel corrosion resistant alloy. That's a very good at resisting corrosion in general, partially due to the passive film it builds up. Hint, hint. But one thing was found is that localized corrosion, again, once you rely on passivity of your metal, you then open yourselves up to, well, what if you push the potential high enough that you actually end up in the pitting region? And so what was found is for alloy 22, over time, maybe after about 200 years after the fuel has cooled down to some degree, you can have seepage from the walls of the mountain itself, such that you have a very corrosive solution dripping onto this alloy 22. There's a paper put out in 1995 that's kind of a seminal paper on this that showed, yes, the drippage that you could expect from the mountain could be enough to then cause pitting on the alloy for your containers. This is one of the issues when you're dealing with conditions that are constantly oxic. You're not able to rely on there to be a depletion of oxygen like you do in the Canadian case where you're burying this deep underground. Instead, you're just relying on the passivity and the corrosion resistance of your containers. So the response to this was, I think this was done somewhere in the 2000s, to add these titanium drip shields to around the actual the containers themselves. So these titanium drip shields themselves were made with a titanium alloy such that they should be resistant to pitting corrosion under this seepage kind of case. Some people have pointed out, again, you're kind of relying on a scenario that's not as robust as, let's say, what we've planned for the Canadian DGR in terms of this multi-barrier system. This drip shield, maybe you could have issues with it, and I don't know, maybe some kind of seismic activity. It's a mountain, right? So it's being formed by seismic activity. It could be degraded in such a way. So, there's been some back and forth about how suitable this is as an actual idea. And so the project overall has been largely on ice for that reason, largely due to public pushback, but there's some underpinning of the underlying science here. So from a corrosion standpoint, this is kind of the inverse of the Canadian scenario. In the Canadian scenario, you have reducing conditions, so you use up oxygen, and you're relying on your container not to form a passive coating. And the reason for this is if it forms a passive coating, you can then potentially enter a pitting scenario. You can't get pitting unless you have passivation first. So you have conditions that are reducing enough that you should not actually form a passive coating. The American case is the flip side. You have constant oxic conditions. There's constantly going to be oxygen present. And you have a scenario where you're relying on the natural passivity and corrosion resistance of your metal. That's the basic change. That's the basic difference between the two scenarios. In my opinion, the Canadian case is more compelling. I'm not going to, again, I haven't done enough. Like my specialty is not looking at what the Americans have put forward for Yucca Mountain. There's people who have spent their entire careers studying and making the case for Yucca Mountain. I'm not one of those people, so I'm not going to turn to you and tell you this is not scientifically sound. But I am going to tell you it's different. It's a different set of things that you're relying on than in the sort of classic Canadian DGR case that we're pursuing in other nations like Finland and Sweden are pursuing. It works differently. And the case for the geology is sort of different as well. That is my understanding. So I will say that we have Canada is in very close contact with our Scandinavian counterparts. Our design of our container actually is more recent than theirs and is based heavily off of their initial design. So we took their initial design, which is very different because they have much more sulfide present in their natural rock form that they have to deal with. And so it's much thicker copper, and it's just a very different design because of that reason. But our design is kind of inspired by theirs in many ways. So it's now I don't know Sweden. I've worked the Swedes quite a bit when I did this research for my postdoc. When it comes to the Finnish, I'm not sure exactly how that's working. But I imagine, yes, that DGR is going to be one of the first commercially operational DGRs that's going to be coming online very shortly. And we can expect there to be some good data on this. Maybe as kind of a small aside, one of the reasons why Finland will be one of the first countries to go forward on this is because they've baked in to their public enough confidence in nuclear in general across the board in terms of public education and public outreach and consultation. So much so that even the Finnish Green Party is on side with a future nuclear build out to try to fight climate change. In most other Western liberal democracies, you don't see that level of public confidence in the technology. But good for them for doing that kind of educational outreach. Great question. So bentonite in this case is relying on being saturated with water. So it works in terms of it works best when it's actually saturated. And in that case, it's actually going to create this pressure that squeezes out all the rest of the water from the container and sort of minimizes any kind of water and air that would be around it. But the Yucca Mountain scenario is relying on the overall mountain being dry, or as dry as possible. And so it's really not bentonite in this case really isn't what you would want. You'd find cracking in it eventually if it was that dry for that long and you sort of keep giving off of it. It probably wouldn't serve the purpose that you're looking for it to serve. But that's a very good question because why wouldn't you just use clay? That's a good question. Any other stuff on this kind of these corrosion mechanisms? Okay, so what if the used fuel container fails? What about the fuel itself? So when it comes to the fuel, the release of over 90% of it, of the fission and activated products, will depend on the corrosion of the uranium matrix. And one of the big reasons for this is that most of those fission products, so actinides like 98%, are actually contained in some way within the matrix of the fuel itself. It's other oxides that are sort of built up around within that matrix mixed in with it. Could not necessarily be within the UO2 itself, but could be within its own sort of oxide form. But it's baked into that actual matrix as it's being formed. There's a couple exceptions to that. There's these metal particles that would segregate likely to grain boundaries. Those are very important. We call those epsilon particles. Don't ask me why epsilon was chosen as the Greek letter. It's just we're going to call them epsilon particles for this course, but they're these metallic fission product particles. And they're very important when it comes to the corrosion of this fuel. And then finally, you've got let's say these grain boundaries and sort of the gap between the fuel and the zircaloy itself and the can lube, and you've got all the stuff that's contained within that. So when it comes to all of this stuff, all the different fission products that are within this gap, the iodine, the cesium, or let's say the iodine that are at grain boundaries, we assume that this contributes to what's called the incident released fraction. So this is less than 10% of the fission products, but what it will do is that we're assuming that it will immediately dissolve on contact with groundwater. So when we're doing our modeling for radioactive release, when let's say one of the containers fail, you're assuming that about close to 10% of that material of those fission products are going to immediately be dissolved. The ones at those grain boundaries and the ones at the within the gap between the fuel and the zircaloy. All right. So we're not going to talk too much more about that because essentially from a modeling perspective, you assume that immediately dissolves, and then it's a matter of the bentonite layer acting as a buffer to its further release, and then you're relying on the other aspects of the overall storage. But we are going to focus on the corrosion of the uranium matrix because its corrosion will control the release of all the other radioactive products, and so we want it to be corrosion resistant. We're hoping it's as corrosion resistant as possible. So this is what it looks like from a corrosion potential point of view. You have your equilibrium potential for fuel oxidative dissolution. So this reaction right here has a certain potential associated with it. And then finally, and then sort of on top of that, you have your radiolysis products. And so they have a potential associated with them, and that's primarily going to be peroxide. So between these, as you would expect, then that's where you're going to have your E-core value that you'd actually be measuring. It's going to be the reduction of these radiolysis products, again primarily peroxide, and the oxidation of uranium. So peroxide is the enemy here. Like that's the out of all the fission products, there's a whole wide range of them. I think I showed you last week. Peroxide's the one that causes you the most problems. It's going to be relatively stable compared to a lot of the other, like let's say radicals, and it's going to react in such a way that it can cause oxidation, and it itself would reduce. So that would be sort of this reaction right here. So rapidly you could have peroxide interacting with the uranium fuel, and that could then be causing oxidation of that fuel and buildup of hydroxide. But what can also happen is these so-called epsilon particles can play a role. So in this case, what they can actually do is they can catalyze the reaction of a peroxide to form hydroxide. So its reduction in a way that doesn't result in the oxidation of uranium. And so this is very important and interesting. This reaction that these epsilon particles can catalyze, because essentially what it's doing is it's removing some of that peroxide from from oxidizing the fuel. The flip side of that would be for O2. So you can have O2 is another one of the radiolysis products we care about, and can be produced in other ways that we'll talk about. But it can form a rapid. It can also go through a similar catalytic reaction in which it rapidly reduces on the surface with epsilon particles. And importantly, this is a rapid process of reduction that it's catalyzed by the epsilon particles, but the reaction with uranium oxide, in which you oxidize the uranium, is quite a bit slower. And so this is one of the reasons why we focus on peroxide as our main concern and not oxygen, because O2 itself, the reaction rates on the epsilon particles versus the fuel are so completely different that we basically assume that almost all of it is going to be catalytically reduced due to these epsilon particles. They play a big role in that sense for what we see for corrosion behavior. All right. So now that we've kind of established the role of peroxide as the kind of, well, not necessarily, I'm not going to say it's the sole issue. There's kind of aspects that we look at for, let's say, carbonate concentrations, but it's a lot less. Oxygen and carbonate are a lot less of a concern compared with peroxide. So here I'm showing you a very important diagram that we're gonna kind of dig into, because I want you to sort of absorb this a little bit more, which is what's happening with the interaction between the surface of the fuel itself, the UO2 fuel, with your radiolysis products in relation to a penetrated container. So we're just going to start off by looking at what's happening on the surface of the the actual fuel itself. So the basic interaction you have here is you have your you have your peroxide itself, your hydrogen peroxide. That's going to then interact with the uranium, a fuel matrix. So it's going to, uranium gives off 2 electrons, and then in the process, you then have dissolution of uranium to the form of uranium-6, and then that's going to be producing oxygen and water as the byproducts of that peroxide reaction. So it's the basic way in which we're going to be getting dissolution of uranium from the surface. This could happen in one step, like you could be forming hydroxide instead, so just giving off 1 electron. But this is what it basically looks like in terms of dissolution of uranium. Is you go from uranium-4 to uranium-6, and then that becomes soluble. And then of course that peroxide itself is formed via radiolysis of water. So that's fine, but what about the role that the steel plays on this surface? So there's some interesting interactions happening when it comes to the corrosion of the steel. Again, from a galvanic standpoint, we would expect really no contributions from copper at this point, because it's going to be more of a noble substance. It's the steel, once these containers are penetrated, in which we're going to see corrosion occur. So if you think about the oxidation of iron, you're going to be giving off iron 2 as the oxidation product. And then in turn, you're going to be forming hydrogen gas within the actual as you reduce water. This is what you're going to be forming as hydrogen gas. This could also happen potentially for peroxide, same kind of idea. But let's assume for this sake that we're forming hydrogen gas. Well, what you can have happen is both the hydrogen gas and the iron, the dissolved iron, can interact in such a way that you actually control the presence of peroxide in the first place, peroxide and oxygen. So if peroxide and oxygen are your kind of attacking species on the surface of the causing corrosion of the UO2 fuel, both can be mitigated by the presence of the corrosion products from steel corrosion. So let's say in the case of iron, you can have an interaction with oxygen such that you further oxidize iron to iron 3. I'm sorry, the red bubble kind of overlaps it a little bit, but you could be further oxidizing iron to some kind of iron 3 compound, and in turn you would get water as the result. And then for the hydrogen, you could potentially have this interacting with hydroxide or a peroxide to then just be forming water. So it sort of negates it. So kind of the important part here is that these interactions can help to further prevent dissolution of uranium oxide from the fuel matrix. So epsilon particles are helping you, and the steel itself, should it become penetrated, is also helping you from a thermodynamic standpoint. So some of the reasons why the actual fuel itself is quite stable under these conditions. Again, you don't get this if you're like in an oxic scenario. This isn't going to help you if like the drip from the mountain penetrates your containers. This is sort of an exclusive kind of thing that you get if you're under reducing conditions. So that's the basic model. I could go a lot deeper into this in terms of what do we see in terms of exposure time to peroxide. I haven't really talked about carbonate at all. That's another thing that we expect to be present, and it's part of what aids dissolution. It's not good. It doesn't play that much of a role in terms of its overall concentration, but it's primarily what's happening when uranium dissolves into the water. It's primarily dissolving as some kind of carbonate complex. But this is the basic model for fuel corrosion. So next we've got the disposal of triso fuel within a DGR. So triso fuel, I think I brought this up before. Certainly I brought it up lots in the last course. But we'll talk about it. And I know all 4 students taking the class all know what triso fuel is, because one of you is studying it, and the other 3 of you took it in my previous class. So it's not like new to any 4 of you. But for other people taking the class who are just sort of observing it, I'll explain very briefly what triso fuel is, some interest surrounding it. So triso fuel is a type of fuel, a composite. So it's where you have not just uranium fuel or thorium or something like that. You've got, in this case, a fuel kernel that is going to be a uranium oxycarbide. It's primarily uranium oxide with sort of a small amount of it being in the form of carbide. That's surrounded by sort of a porous buffer layer, then sort of a high density a pyrolytic carbon layer acting as sort of a physical structural barrier to make these little particles really hard. And you have silicon carbide that acts as a barrier for fission products to be released when the fuel actually undergoes fission, and then another pyrolytic layer for further structural protection, all surrounded by graphite that acts as a moderator. So it has a couple of things that it's really good for, which is that it performs really, really well in a reactor scenario. You have essentially full containment of the fission products, not completely. Some of these particles can break, and silver is sort of nasty for getting through silicon carbide. But you've got your almost entire control over fission products within this fuel. And you can bring it up to very, very, very high temperatures. People often call it meltdown proof, if you will. When that, I don't know, take that for what you will. So this is a very robust, and from a disposal standpoint, yeah, Westinghouse is planning on using it. They're kind of a major player here in Saskatchewan with their design. From a DGR disposal scenario, it's got very good performance. We see when we look at the overall fuel kernels themselves, but these aren't experiments that were done. These are experiments that are done under nice control conditions, but what they haven't done so far is looked at the individual components. So all that great electrochemistry I was showing you before, where we know the passivation potential, and we're very confident that the thermodynamics are such that the overall fuel should be very stable. That work hasn't been done for this. So that's a major focus of Brett's work, and some other students over at Western, and somebody else, another student I'll hire at some point. But there is a gap right now when it comes to the knowledge basis for how this stuff, each of these individual components, perform in a DGR scenario from an electrochemistry standpoint. From a pure kinetic standpoint, it looks really good, but so did alloy 22. Looked really good from a kinetic standpoint until you started looking into the electrochemistry and thermodynamics and realized, oh, oopsies, this isn't going to cut it. So that's a focus of our. It'll likely be fine. Even if it should be at least as good as. I'm likely it's going to be at least as good as CANDU fuel, but we need to look into it. So that's something I'm bringing up anyway because there's a gap there. But this is another sort of form of fuel that we're interested in depositing within the DGR. I haven't really gone into this too much, but it's kind of noteworthy that there's no really good electrochemistry that's been done for this so far. It's all kinetics. When you're dealing on a time span of 1 million years, you probably should not be relying on kinetics. If there's anything else you're taking away from Professor Situm's little diatribe, that's the diatribe. Don't do it. Don't just say no. Do thermodynamics. Next bit here, a couple of slides left, and then we'll spend the rest of the lecture doing a review. Classes of radioactive waste. So Mehdi brought this up very briefly. For this lecture, we've been primarily focusing on CANDU fuel, and it's sort of its relation when it comes to the DGR. There's many other forms of waste, though, that are dealt with, most of which is going to be this sort of so-called low-level waste, mop heads, very, very slightly contaminated materials. You can have intermediate level waste, would be these sort of spent ion resins that are used to actually filter any kind of a crud from the, and I do mean crud, from the primary circuits of reactors. Those end up having some activated products in carbon-14, and they're held as intermediate level waste, and they have to be dealt with. That's a research project that me and Mehdi are working on in terms of how that's going to be managed within a DGR. But generally, when it comes to the high level waste, this is what's been mostly the focus for Canada when it comes to the DGRs. Couple other notes here. So some things that Saskatchewan will need to think about, or Canada in general. When it comes to low-level waste, you typically dispose of it within sort of one of these so-called near-surface disposal facilities. This is sort of some kind of simulated 3D model of what it would look like for Chalk River. They have an approved near-surface disposal facility now being built. And for intermediate level waste, as well as high-level waste. So it's spent fuel and other nasty research stuff. For that, it's been mandated that you need some kind of DGR. So it's an open question how that's going to work, particularly when it comes to intermediate level waste. So with that kind of covers things off. So we were not going into intermediate today, but I do want you to be kind of aware of what does and does not, what is and is not applicable to DGRs. That's what I'm trying to get at here.